Okay, so a particle moves along a straight line such that its position relative to a point is given by the formula. So that's its position. All right, so the key here, if that's my position, my velocity is the rate the position changes. So velocity is dx dt. And dx dt here is 18t squared minus 9. So that's my velocity rule. All right. When will it have zero velocity? Solve that equal to 0. I get t squared equals 9 on 18. So t is equal to plus or minus a half. Yeah. Oh, what's over there? Sorry, plus or minus root 2. Already got that. But given time, negative doesn't make sense. So t is equal to 1 on root 2. So if I put 1 on root 2 into my position equation, the x equation, 6 times 1 on root 2 cubed minus 9 times 1 on root 2 plus 5, I'm going to end up with 5 minus 3 root 2 meters. So that's where I am when my velocity changes. The acceleration at those instances, well, if I want to find acceleration, that's the rate that the velocity changes, dv dt, which is my next derivative. So the derivative of the velocity rule is 36t, and at t equal to root 2 on 2, my velocity is going to be 18 root 2 meters per second squared. All right, keep moving. Obviously, we've got access to a CAS here. If c of t is equal to 5 on root 2 t e to the minus 3 on 2t, find at what times is the instantaneous rate of change, instantaneous being the actual derivative, when is it equal to the average rate of change? So my average rate of change over that interval is y2 minus y1 over x2 minus x1. So substitute 3 into the function, substitute 2/3 into the function, over 3 minus 2/3, and I get negative 0.22706. So then I want to know when my instantaneous rate of change is equal to that. So if I solve the derivative of my c of t equal to negative 0.22706, I will get x equal to 0.90 or 2.12 centimeters. All right, this one without a CAS. So the temperature in a room is followed by T of T equal to 20 over 2T plus 1, where T is the time elapsed in minutes. All right, so as T increases, my temperature is gradually dropping. So maybe we've turned the heater off. Calculate the value for the rate of change of temperature when 5 minutes has elapsed. Calculate the rate of change at the 5-minute mark. So that's the instantaneous. So D, capital T for temperature, lowercase t for time. So T dashed of T, if I differentiate, minus 1 comes out the front, 20, 2T plus 1, take 1 from the power, multiply by the derivative of the inside, which is 2. I end up with negative 40 over 2T plus 1 all squared. So that's my instantaneous rate of change. I'm interested at T equal to 5, which gives me a negative 40 on 11 squared, which will give me a negative 40 on 121. All right, so if we want the average over the first 5 minutes, there's my average rate of change. So T of 5 minus T of 0 over 5 minus 0. So it's that y2 minus y1. T of 5 is 20 on 11 minus T of 0, which is 20. All that is over 5, of course. Just get a common denominator there. So we'll have 20 minus 220 all over 55 if I put the 20 on 11, which is negative 200 on 55, which gives me that negative 40 on 11 degrees Celsius per minute. All right, so now we've got a balloon leaking and it's decreasing in volume. Its volume is given after t seconds by V of t equal to 600 minus 10t, not 1 on 10t, so there's a little change there, minus 1 on 100t squared. All right, so notice that, so we can match off with the answers that have been given. So we want to find the rate of change of the volume after 10 seconds. So after 10 seconds or at the 10-second mark, that's my instantaneous rate of change. So I'm going to need dVdt, which in this case is negative 10 minus 2t on 100. Obviously, the point I'm interested in is at t equal to 10. So put that t equal to 10 into there, we get our negative 10 minus 20 over 100, which is a negative 10 and 1/5 centimeters cubed per second. So the rate of decrease, again, the change in dVdt after 20 seconds. So at t equal to 20, put that into the same rule. And I'm going to have negative 10 minus 20 on 50. I'm trying to work out what I've done there. Negative 20 on 50 instead of 40 on 100, which is negative 10 and 2/5. But because we've been told it's a rate of decrease, our answer is positive because a decrease itself implies a negative value, yeah? So it's positive 10 and 2/5 centimeters cubed per second, all right? Then we have our average rate of change from 10 to 20, average rate of change y2 minus y1, x2 minus x1. So that's that v of 20 minus v of 10 over 20 minus 10. So we substitute those values in, we'll get 600 minus 200 minus 4, subtract 600 minus 100 minus 1, all over 10. So 396 minus 499 will give me negative 103 on 10 centimeters cubed per second. So that's my average rate of change.